Morning. My name is Mary Napolitano, and I am the product manager for LinacView. And today I'm going to talk a little bit about why you should use LinacView for every fraction of every treatment. Today's webinar will be recorded for your future review. At any time, you can enter questions into the GoToMeeting dialog box, but I will most likely not answer them until the end of the session. I wanted to let you know that Standard Imaging is based in Middleton, Wisconsin, and was founded in 1989. At Standard Imaging, we design and manufacture a full suite of QA products. And here you can see some solar panels behind the building. Standard Imaging is a green company, and we also have geothermal heating in the building. So during my presentation, I will begin with an overview of the basic workflow, a quick look at the software, and then provide a bit of background on log files and how and why they are useful for patient-specific plan comparisons, where we compare the RTPlan and the log file. I'll show a few examples of Fluence-based comparisons for both gamma calculation criteria pass and fail, so you can see how that would show up in LinacView. Then I'll discuss a few recent publications comparing Logfile versus detector arrays, and finally I'll review some of the advantages of Logfile analysis software. So here's the basic information flow for LinacView. So you start, with the treatment planning computer and exporting the RTPlan. The RTPlan is exported both to a batch folder that LinacView monitors and picks up and imports those RTPlans. And then as well, the RTPlan, of course, is exported through the pathway to get to the Linac console. And then the log files are then monitored by LinacView, again, an automated process, such that any RTPlan that has been picked up by LinacView will automatically associate and analyze the log files that are automatically picked up from the Linac. And so just to kind of show you how LinacView would be used in the clinic on a day-to-day basis, I wanted to show you briefly the view of LinacView that would be seen on the computer that is typically maintained near the Linac console. So let me pull that software over. And right now I have a blank dashboard because we haven't started treating patients yet today, but the RTPlans are already picked up by LinacView. So I'll just go ahead and the Linac is up and running. So I'm using my simulator to send some log files into the system. And right now I'm sending in a session that is a prostate plan. It's a single arc, and I have sent in sessions from 6 different days. So you can see how quickly each session is analyzed. This is an entire treatment session, and you get the results right away, pass, pass, pass. And you can see that there is not much data showing, but this is just a basic user login, and it's not the physics login. And with the physics login, you could go in and do a lot more analysis. I'll send in another plan just to show you that this is a 9-session plan. So it'll take just a little bit longer to analyze. And it has 2 arcs, and each arc is analyzed separately. It's also an RTPlan that has keywords, and you can see this template I've set up is Electa Complex. So this is an Electa Linac, and it's a more complex plan. This plan specifically, as analyzed by LinacView, shows a modulation complexity score of 0.190 for the first arc and 0.273 for the second arc. And what you notice, if I can get some of my screen cleared, because I have a lot of things blocking my view from the webinar session, you can see that the second arc has failed for all of the 5 sessions. Whoops, sorry, not arc 2. I have more things covering my screen. So neither arc has, let's see, shows failures for this plan. So this is completely passing. So I'll pick another session to show you some failures. So all 9 daily sessions for each arc shows pass rates. So let me pick one that I know will fail. Okay, so this is a 5 session plan, again with 2 arcs, and the modulation complexity score for this one is 0.219 and 0.123. So just a little bit more complex than the last one. This is a head and neck plan. And again, it's using this template that I call Electa Complex. And as you can see, I'm receiving some email alerts, and as well, you see the session failure for this plan, all in ARC 2, which is the more complex plan. This is 5 different day sessions, so 5 different emails will come through. Clearly, these would, have come through on 5 consecutive days. And so these emails will continue to alert. And so you can see it's just ARC 2 that has the failures. And then at this point in time, if the physicists were in the break room, if they were working from home, they would know there was a plan failure right away at the treatment console, or someone could call. And there is also an audible alert, but I prefer to keep mine off. If you were really using this in the clinic, you would have your audible alerts on and be receiving those as well. In addition, if you just kind of hover in the area, you can get some details pertaining to the plan comparisons. And so you can see here that the Fluence comparison, we had a 92.3% pass rate. And so that was below the 95% pass rate. So you can get a little bit of information, but usually the physicist would log out of the basic user. You can see we're logged in as a basic user, and log in as an admin user, where you can see more information like the Fluence maps and everything. So that's what I just wanted to show you, how that would actually be set up and working in the clinic in the treatment console area. And so just, to get you oriented, so the RTPlan, of course, has control points, and then the log file is monitoring the plan delivery. And there is more granular information associated with the log files than there is the RTPlan. So now I'd like to go into some more details about the RTPlan control points, which are much more sparsely spaced, and then discuss a bit further about the log files. So log files were initially generated, as logs are for any software, to record the delivery based on feedback mechanisms designed into the Linac. The feedback from the monitor unit chamber, the MLC positioning feedback mechanism, as well as the JAWS gantry and collimator. And then, of course, when these are out of tolerance, as the Linac is designed, you do get beam off until, in some cases, the leaves catch up to the position they should be based on the control points, and it's back in tolerance. The Electa Linac decreases the dose rate whereas the variant actually beams off. And these, of course, were originally intended for use by the Clinac engineers, but there's a lot of great information associated with the log files that we can use for QA purposes. And there are different types of log files for the different vendors, clearly, and even between the different models. So the variant Clinac has the Dynalog files. The TrueBeam has trajectory log files, while the Clinac has TRF log files, but those are not accessible by external vendors. They can be accessed after treatment and manually exported, but we are set up in LinacView to be a real-time system so that you want to be getting those log files right away. So external external vendors are required to use the ICOM VX interface for Electa. And so with the ICOM VX interface, the data is streamed out, and we collect and save that data as the log file for Electa Linux. I wanted to just go briefly into the sampling rate because that varies as well. And the sampling rate is records per second and varies by Clinac model and vendor. The Clinac series has 20 records per second, the TrueBeam and the Halcyon 50, and the Electa ICOM VX system has 4 records per second. So back on track, log files can be used to make direct comparison of multiple parameters such as the jaw positions, carriage positions, MLC positions, gantry and collimator angles, monitor units, as well as the beam states, meaning beam hold or on off. And then as a clinical physicist, so what does all of this mean? How do I associate misalignments of an entire bank, offset versus a few single leaf positioning tolerance variations? So in order to provide this link, one can directly calculate the delivered fluence as recorded by the Clinac using the log files. So primarily we're using the MLC leaf positions and the fraction of the total monitor unit to calculate the delivered fluence, and then compare that back to the planned MLC leaf positions and monitor units. So once you understand in general the information coming from the log files, the next step is to be able to map the log file record to the RTPlan control points. And this is easier or harder depending on the log file type. For example, the variant, the Dynalog file versus the does not have the fraction of control point within the log file, whereas the other version of the variant log file actually specifies fraction of control point delivered, so it's very easy to map. The same fluence calculation then can be performed on the RTPlan such that there's direct 2D fluence comparison using the traditional gamma analysis between the planned and delivered treatment. The RTPlan specifies delivery based on control points, and only at these control points is the configuration specified. So then between those control points, the movement of the MLC is not specifically defined, and so one assumes that there's uniform leaf movement and uniform dose rate between the control points. And there are also features in LinacView that allow you to create an RTPlan based on the selected number of control points up to the actual number of points specified in your log file. So now I'm going to transition into some sample fluence comparisons from the RTPlan and the log file. So here's the RTPlan Fluence map, the Logfile Fluence map, and then there's also a histogram displayed. This is, of course, the gamma index versus the percent of Fluence comparison pixels. And for this plan, we have gamma 2%, 2 millimeter, cutoff of 5%. And you can see here in green is specified the 99.7% pass rate. The Fluence maps are created by projecting the MU-weighted segment to the isocenter plane. And, you know, if the specified tolerances is not exceeded, there is no action required for this session. Just, you know, review as the session's complete and the entire treatment is complete. So the next case is a 3-arc breast plan delivered on TrueBeam. Of course, here at the top, we see the RTPlan Fluence map, and at the bottom, the Logfile Fluence map. Here we have, again, 2%, 2 millimeter with a cutoff of 5%, gamma pass rate's 100%. So as long as you have a well-commissioned system and you keep up with your machine QA, the vast majority of plans will not generate any sort of alert. One gets confirmation as each session is delivered, and then a summary report is generated when the treatment ends. So in general, good results are not surprising, as there is no setup uncertainty, no finite space detector grids, etc. So I wanted to show you a few screenshots from a case where LinacView shows a failure, because you would need to go in and further review the plan. And so these are some of the screens and parameters you could review. So this Head&Neck plan has a modulation complexity score of 0.074. It's a highly complex plan. The lower the MCS, the more complex the plan. This plan was delivered on a variant Clinac, so it's an older machine, so one might expect more performance issues. This particular plan had alerts for 2 leaf-related metrics, the RMS leaf and maximum deviation alerts. And so you can see here, this is the RMS error for the banks. And you can see in red the tabular specifications for the bank, Bank A and Bank B. For example, leaf number 10, the bank RMS error is 1.7 for Bank A, 1.8 for Bank B. We have also graphical representation. Leaf number 10, you see the same data up in this area with Bank B in purple and the Bank A in an olive color. And across here is the failure threshold set at 1 millimeter and the alert at 0.75. And so you can see for a large portion of the plan, the bank RMS errors out. You can see as well up here for a particular leaf. You can look at leaf number 10 and review as RTPlan control point the leaf position deviation in millimeters, both positive and negative for each bank. And so it's just kind of an interesting view. If you're having plan failures, you can go in and look at lots of statistics to unravel the mystery. And of course, you can look at your traditional, gamma comparison map. Here you can see for 2%, 2 millimeter, an 88.5% pass rate. You have the histogram, the gamma map in this area. These are below the threshold is this blue, so that's below the 5%, but you can see the yellow in this area, which is above your gamma of 1. So you can look at the traditional metrics as well as go in and review other details should you so desire. It's color coded, so it's easy to go straight to the errors. This is the tab, you have information and it's color coded. This is what you're monitoring, the beam off, collimator, gantry, Fluence versus plan, MU and leaves. The ones that pass are in green and fail in red. So you can just hone right into the area that you need to review. The next Fluence comparison is for Halcyon, just because it's one of the major new features released near the end of 2020. And so these results are for a Halcyon head and neck plan with 2 arcs, not too complex of a plan, modulation complexity score of 0.26 and 0.282. It has 2 arcs. All the alert and fail criteria parameters are passing. A really great mean gamma, 0.066, 2% 1 millimeter, and 99.5% pass rate. And then, just so you know, there are different screens to review both the distal and the proximal leaf bank errors, both on a leaf-by-leaf basis as well as the entire bank. Unlike the previous case I showed, we're well below the alert and failure limits. But, so the Halcyon's a nice new machine. You expect good results, but we have had customers that have seen some errors shown by LinacView. So it is a valuable tool, particularly for these, more these adaptive workflows where you'll perhaps be changing your plans, or you need to have an independent QA method. So I wanted to go next into talking about a few recent publications that provide comparison between Logfile-based and detector array-based patient-specific QA. So one is an AAPM meeting poster up here at the top, and then the next 2 are articles from the Journal of Applied Clinical Medical Physics. So we have links to these articles on our website, so you can find them there, or reach out to me and I can send you the links. So the Logfile solution is found to be, and I quote, very sensitive in detecting small delivery errors. And Logfile analysis, to quote from the 3rd article then, is, quote, provides a robust and reliable QA method to reduce patient-specific QA measurement, provided that a comprehensive measurement-based machine-specific QA program is in place. These types of analysis programs provide end-to-end plan transfer as well as beam delivery checks. Physicists must always make sure that machine-specific QA is carried out. So I would like to share with you some specific data reported in the first reference. For this study, there were 66 plans delivered on an Elekta Unity, and these plans were analyzed using LinacView and measured with a commercially available detector array. 11 of those plans were incorrectly matched to check for error detection sensitivity. So for those of you that may not be aware what the Elekta Unity workflow is like, every day there is a plan of the day. So each day the plan is adapted. So there'll be a day 1 plan of the day, a day 2 plan of the day. And so what was being studied was if comparison between, say, the day 1 plan that was approved and inadvertently delivering, say, the day 3, actually the day 3 plan. And so we're seeing if incorrectly matched plans would be detected. And so for the correct plan, the gamma 3%, 3 millimeters, for the detector array range from 94.7% to 100%, and with LinacView 95.4% to 100%. So, correct plan works well. Both systems show you excellent pass rates. And then, but the one that's, of course, more interesting here is the incorrectly matched plans. And so in this case, say a day 1 plan is compared to the delivery from a plan on day 3 or even day 2. And so the detector array showed gamma pass rates of 3.9% to 84.8%. And so clearly, you can see some failure going on here. LinacView, though, showed 1.2% to 21.7%. And so these were all, quite clear failures and more sensitive than the detector array. And in the paper, the abstract showed that significant rank correlation between log file analysis and detector-based measurements. And to quote from the paper, the log file analysis can provide higher throughput to automation, but can also provide faster patient-specific QA feedback to clinicians and physicists. And you saw the speed of analysis when I was demoing the software. So advantages of log file analysis. Of course, you could use it for pre-treatment QA, but really, the software is designed for automated QA as part of every fraction for every patient. So you could use it for both functions if you so desired, but the real design intent is for every patient every day. You get automated notification of the console as well as email alerts. And for the adaptive workflow, log file analysis is key because it's time consuming keeping up with detector array-based PSQA for every adapted plan. But it's got great utility for non-adaptive workflows as well, for patient safety aspects. The Clinac, the log file analysis has been shown to be more sensitive than detector array analysis. So in summary, I hope that I've convinced you that there is a wealth of information available for analysis within your log files. LinacView software maps the RTPlan control points to the log file data. Gamma analysis of the Fluence comparisons occurs between the plan versus the delivered. Comprehensive analysis tools are available. As well, log file analysis is more sensitive in detecting errors compared to detector arrays. And log file analysis advantages are numerous for all treatments, but in particular for the adaptive workflows. So thank you for your time and attention, and I'm sorry that my printer was acting up a bit during the presentation. But that concludes my presentation, and please go ahead, if you haven't already done so, type any questions into the dialog box and I'll do my best to answer them. So the question is, how can we treat the errors? And what are the possible errors? So what you would do is, if your leaves are not moving at the desired speed, not really keeping up with the plan, then of course you can, call in your, your Clinac engineer and calibrate a bit better. Of course, you can review your modulation complexity score. If it's an older Clinac and your leaves really are not keeping up, you might decide to keep an eye on the complexity of your plans. For example, if you have an old Clinac, you should ask the planners to back off on the complexity of the plans so that you will actually be delivering what you have intended and planned. Other things happen, like the gantry motion. That's a known issue at the start of some treatments in older Clinacs, and so you might just have to see that, oh yeah, the gantry mechanism is sticking a bit, and we need to go in and have some maintenance done. But mostly, I think it's a lot of it has to do with the complexity of the plans and the age of your Clinac. And you might start seeing things that would indicate, if you're getting near your alerts, it might be time to have some Clinac maintenance performed. So one of the questions is asking, why is the gamma index not 100%? What are the errors? So, you know, the RTPlan, I would call it it's theoretical, right? You have a specific control point and a specific monitor unit, and the Linac itself has a certain tolerance associated with it. And, you know, those tolerances are great and they are built in, but there is just some difference in the actual treatment versus the planned treatment. Mostly it's very small. And so in most cases, your gamma pass rate is going to be very high, you know, 99% or greater. But the leaf and the monitor units aren't precisely what are specified in the plan, you know, for any real system. The errors are small, and the Linac feedback system keeps them within a certain tolerance. But LinacView allows you to bring specific leaf-by-leaf information and monitor unit information into the analysis. I hope that answered that question. Let's see what other questions we have. I think I've answered what are the possible errors. What will be the gantry angle at 0 degrees? I mean, the gantry angle is at whatever position the plan specifies. The gantry angle is a separate parameter that is monitored and is not incorporated into the Fluence comparison because it is a comparison of the Fluence coming out from the Linac head. So the gantry angle is analyzed as a separate parameter, and you would want to have that specified separately in order to catch gantry angle errors. What can we do as a better commissioning test for log files, for using the log files? Well, I've seen a couple of interesting things out recently in some journal articles. One group in particular, they used their EPID panels, and they determined that just straight use of the EPID panel comparison was not giving a true representation of the leaf position. And so they had to include some ghosting corrections because they were actually being misled by the EPID images they were taking directly from their panel. And so you can do comparisons with your EPID panel with specified leaf-specific induced errors. Of course, I think I gave some examples early on about papers that were doing detector array comparisons and showing how a lot of small errors could be determined using detector array comparisons. Those, of course, there are multiple articles that you would you could review. So I think that's all the questions. I hope that was clear. And please don't hesitate to reach out if you have further questions, either to your sales rep to get in touch with me, or you can contact me directly. My email address is mnapolitano@standardimaging.com. Thanks, and have a great day.